Good morning. I think that we can wait some minutes, maybe 2 or 3. Okay, good morning once again. It's a pleasure to meet with you today during our second meeting on statistical data analysis. Today we will be talking about testing hypothesis, statistical testing hypothesis, statistical verification of hypothesis, also about random variables, and also about some methods which we can use for measuring relationships between values of different variables. It will be this third topic also will be our main topic for tomorrow meeting. So first about random variables. Random variable can have random variable for random variables. When we want to define random variables, we can define sorry random variables. In random variables, random variable, it is a variable which can have different values. And for every value, we can define the probability that this given value is assigned to this variable. How to generate them? First, please look at this example. I think that you see my screen. It is a very short program which I use for generating a series of random values. We will be talking today also about some details concerning generation of random variables, but now it is enough to know that these random data are generated here using this command which we have in the second line. So please, we can run this program, and we see that these data, random data, which were generated using this command, I will talk about this command in details in some minutes, were assigned this data to this object, my data. Here it is only for transforming this data into data frame, and the name of this column, it is a data frame with one column values. This name is defined here. And we see here the results. So it is a series of random values. We can treat this column as values of random variables. Random because all values which we have here were generated using some methods for generating random values. Also, it is possible to say something, and we will try to do it in some minutes, about probabilities of occurrences, probabilities of appearing for every value. For example, we can we can specify, define the probability of obtaining these values which we have here. So here in this example, this random values were generated, so it is an artificial data set, not real, but we will use in some examples these artificial data sets. But the same procedures we can use for real data. So we see how to generate. It is one of the simplest examples for generating random values. And how to describe these values? Because here I generated a series with 1000 elements. So of course we can display them, but it is difficult to analyze a lot of numbers, great number of numbers, and we should have some methods for describing these random values. Of course, also it is rather difficult to define, to calculate the probability of obtaining of every value. To say the truth, in this example, these probabilities are zero because it is continuous random variable. Also, we will say about it in some minutes. So first, I would like to show you some other methods which we can use for describing random variables using this data which were generated here. So we will treat this data as a random variable, and now we are thinking about different ways of describing these values. I think that the simplest form of describing values of random variables is to plot this diagram, which is called histogram. We see here histograms. Please look at these values. Here we see two parameters, low and high. These parameters are used for defining the smallest and the biggest value which can be generated. So all values which we have here as values of this random variable are from this interval, from this range, from 0 to 10. And now how we should build histogram. We have this range, 0 and 10. So it is a minimum value which we can have in our data set. It is a maximum value which we can have in our data set. And after it, this range from 0 to 10, we divide it into some equal intervals. In our case, it was divided into 10 intervals. So from 0 to 1, from 1 to 2, from 2 to 3, and so on. We have 10 intervals. And after it, we calculated how many values are in every interval which was defined. For example, in this data set, we have values from the interval from 0 to 1, and the number of these values from this interval we see is about 100. I think above 100, maybe 105, 110. And for every interval, we can calculate the number of values which belonging to this interval. And in this way, we created a histogram. Here on the x-axis, we have the count, the number of observations, and its value is very often described as count of elements in every element, in every interval, or frequency. Frequency also in this context means the number of elements in every interval. And we see how many values we have in every interval. We can generate this plot. I use this code for generating it. So it is very, very, very simple. To the simplest histogram, we can we can generate using only this first command. It is here SNS means Seaborn package. It is a very good package. I think that maybe you know this package for graphical presentation of statistical data. And we see these values here. This information about the distribution, about these values. Distribution means the way in which these data are divided into every interval. I think that you used this form of graphical presentation. It is the simplest form, and also we can use, please look at these two histograms. They look very similar to each other. We can say that they are the same. But of course, there is one difference between them. This difference is related to y-axis. Here we have integer numbers, and we know how to interpret them. It is a number of values in every interval. Here we have density. Density, it is rather real numbers, rather small numbers, and we should know how to interpret these values. These values which we use for describing the density. Here I put, I think, the simplest definition of density. It is a number of objects in every interval divided by the whole number of objects. So the whole number of objects here in our data set is 1000, and you remember in the first interval we have above 100 objects, so we see that density for this first interval, for the first range, is something above 100 divided by 1000, and it is something above 0.1, maybe 0.11, something which is very close to this value. So the only change which we can observe using this and this forms of histogram is related only to this y-axis. So these values, we can say, were scaled. But this histogram, which we have as density, with density values, this histogram has very interesting feature. We can sum up all these values, which are represented by every bar, by every rectangle at this plot, and the sum of all of them is always equal to 1. So after summing up all these values, we always obtain 1. Also, we can interpret it in similar but slightly different way. We can say that area of all these rectangles are equal to 1. And this feature also will be very, very important for us. So it is density. It is density, but presented using histogram plot. Very often we use other forms of for presentation for density presentation. Density, it is very important element, feature, characteristics, which we use for when we want to describe distribution of random variables. So now we can move to this very, very important concept, which is called distribution of random variables. How to present distributions? But of course, first we should define this concept. Distribution. Information about the way in which data are shared out, are divided among different intervals. Sometimes we can say about intervals, sometimes about ranges of values. So, of course, our histogram, which we had here with density values, is a very good form of presentation of distribution. It is very good, but also very simple form. So we see that we can use you can use histograms for presenting distribution, how data are divided into every range which we have in our data set. And we see here how they are divided. So here we have the range for all data from 0 to 1. We have divided it into some ranges, and we calculated the number of occurrences. So formally speaking, histogram, it is a very simple but also very useful form of presentation of data distribution. Data distribution. Here we have continuous random variable. It means that any value from this range between minimum and maximum points, values, can be assigned to this variable, any value from this range. It is continuous, sometimes we can say real variable. And histogram, it is the simplest form for presentation of variables distribution. But also, we have some other ways of distribution presentation. And I think that the most popular form of presentation information about distribution is probability density function. Probability density function. This function informs us how likely for this real random variable is that a given value of this variable fall within a certain range. So we see how these values are distributed among, maybe between different ranges, different intervals. And I, I will return to this picture. And this probability density function we can have this probability density function in two forms, theoretical and empirical. Theoretical, when we are talking about mathematical backgrounds of our distribution. So we know some mathematical rules which are used for generating this random data, and knowing these rules, on the base of these rules, we can define this distribution. And empirical distribution is calculating using a given data set. And of course, we can compare empirical and theoretical distribution. And for our data, which were generated at the beginning of our today meeting, we can build this empirical distribution in this way. So it is an empirical distribution for this data. Of course, it is estimated using some statistical methods. I will show you this method, which is used for generating these plots. So we see the shape of this distribution. The shape of this distribution, of course, is similar to the shape of this picture. We have here values from 0 to 10, and here we know how to interpret these rectangles. It is a number of elements from every interval, from every range. And here, the way of interpretation is the same. But we have this shape, and if we want to know what is the probability that, for example, a given value of this random variable is belonging to the range from 2 to 6, for example, from 2 to 6, then we should draw here, we should calculate the error of this figure which we have under this curve. So maybe here we see here theoretical distribution, but maybe it will be easier to interpret. So, for example, what is the probability that the data is from -infinity to 1? That a given value of this variable is from this range, from -infinity to 1. This probability is equal to this area which is under this curve, and which is here presented using this gray color. So it is theoretical distribution. Of course, we can say that this plot was uh, was very good, but this distribution, it is not maybe as beautiful as this one because it is empirical distribution, calculated using our data set. How this distribution is estimated. Please look at this picture. We have in our data set some values. In our data set, we have 1000 values. On this picture, we have only some values. It is maybe here we have values from different range from 0 to 80. And these values which we have in our data set are here uh, represented by these small marks which we have on x-axis. Here we have these points, which are from our data set. And after it, we draw this curve. It is called Gaussian or normal curve, this, which is located under every point. So the highest point of this curve, this bell curve, because it is similar to a bell, is located, the highest point, always under the value which we have, under every value which we have in our data set. So on under every mark which we have here, we have one this bell-shaped curves. And after it, having these orange curves, for every point which we have here on x-axis, we should add all values which we have under this point. And we, after summing up all these values, this value which we can obtain in this way are presented by this blue line. So for example, for this point 20, we can draw a line here, vertical line, and to get values in which this vertical line crossing all these orange lines, we have some values, they are about, I think, 0.06, 0.07, and sum all these values. And 0.006, 0.008, and we should add all of them. And this aggregated value for a given point, for a specific point, is presented by this blue line. And this blue line represents the function which is called probability density function. Probability density function. So having this function, we can calculate the probability that a value of this random variable belongs to a specific range. But we should remember that if we want to calculate this probability, we should calculate the area under this, in this case, blue line, under this blue curve for this range. For example, what is the probability that a value of this random variable, which is presented here, belongs to a range from 20 to 40. We should draw these vertical lines here and calculate the area under this curve, blue curve, in this region, in this range from 20 to 40. It is the way in which we should interpret probability density cancel. It is not allowed, it is not proper to say that the probability of occurrence of value which is equal to 20 is defined by a position of this blue line under this point. No, it is not allowed to read a y coordinate for this point and interpret it that it is the probability of occurrences of appearance for this value. Because for continuous random variables, when we can get any values from 0 to 8 in this case, a probability of occurrence for one specific value is always equal to 0. Because when we draw a rectangle and the length of this line, horizontal line, is 0, then the area of the whole rectangle is always 0, because we should calculate the probability of occurrence of a value which is equal to 20 as an area under this curve in the range from 20 to 20. The distance from 20 to 20 is equal to 0, so the area also, the size of this area also is equal to 0. So we know how to interpret probability density function, how to estimate it, how to interpret it, but also we should remember about one very important condition. The area under this whole curve is always equal to 1. So the area which we have under this blue line, so this shape which we have under this blue line, the area of it always is equal to 1. It is a necessary condition for interpretation of the area for a given range as a probability. Because the probability of having a value from the range from 0 to 80, in this case, always is equal 1. So we should remember about scaling this this y-axis. We should always remember about it. When we use this command for plotting this probability density function, it will be conducted automatically. So we know we know probability density function. And this way in which probability density function is estimated using many bell-shaped curves located under every point is called, this method is called kernel density estimation. Kernel is represented by every orange line, by every orange object which is located under every point which we have in our data set. So for our data, we see this empirical distribution function. This empirical distribution function, which was estimated using this method which I presented here, kernel density estimation method. So for every point, how to do it? We can draw an x-axis to mark every point which we have in our data set, 1,000 points. Under every point, we can draw this curve, this bell curve, and after it, we should sum up values under every point which we have in our region from 0 to 10 in our case. And then we obtain this shape. And finally, we should change values here. We should normalize these values in this way, which assures that the area of the area under this curve is equal to 1. This area which we have here is equal to 1. Of course, I think that we see similarity between this shape which is presented here and this shape which is presented here as a histogram, because the same information is presented on these two pictures. So it is probability density function. Also, we have another method, which is called cumulative distribution function. It is the last method which I'm going to show you today. Cumulative distribution function, it is a different way of presenting distribution. And here we see on this picture probability density function. And here, this shape which we have here, this which is similar to S letter, it is a cumulative distribution function. How to interpret these values? Cumulative distribution function, it is a function which allows us to calculate the probability that the value of a random variable x is less or equal to the specific values. For example, we have a probability density function, and we know how to calculate the probability that a value of this variable is between -1 and +1. We should draw these lines and to calculate the area after this line, this curve, in this region, in this interval from minus to +1. And cumulative distribution function has very similar interpretation, but the left limit for this interval is equal to minus infinity. So when we want to know what is the probability that a value of our random variable is from the range from minus infinity to, for example, 1, we should calculate this, the area of this figure, which is here presented using this gray color. And for every value which we have here on x-axis, we can calculate this probability. What is the probability that a value of our random variable is smaller or equal to this specific value, which we have on x-axis? And these probabilities are presented here using this S-shape function. For example, we see that the probability that a value of our random variable is smaller than 1 or equal 1 is about, I think, 0.15. What is the probability that the value of our random variable is smaller or equal to 0? It is 0.5. And of course, it is obvious because we have 0 here, so we can draw this line, vertical line here, and the area which we have under this curve on the left side is equal to 0.5, because it is a function symmetric with respect to this value 0. Of course, sometimes we want to know the probability that a value of our random variable is greater than specific value. What is the probability that a value of this x variable is greater than 1? Of course, it is equal to this area, which is here marked using this white color. So we can calculate it, or we can calculate this gray area and subtract this value from 1, because the area for the whole line is always equal to 1. So 1 minus cumulative distribution function is a probability that a value of a random variable is greater than a specific value. And these three forms which we have here are very useful when we want to present information about random variables. So, of course, very often we can use some formulas, and I will show these formulas, which we can use for calculating the position of every point on this on these lines. But we will see that these formulas very often are very complex. And when we see these formulas, sometimes it is difficult to interpret them. But having these three forms of description of random variables in graphical presentation, we can say a lot about values of this random variable. So these three forms of presentation are here: histogram, probability density function, and cumulative distribution function, which is a transformation of probability density function. And here I generated a plot of cumulative distribution function for our data. It is, we see, very, very simple plot. Now, having these three tools of description of random variables, I'm going to show you some types of distributions, which are very popular in statistics. Uniform distribution. Our data, which we use in the first example, are generated using this distribution, uniform distribution. How to define this distribution? When we want to define uniform distribution, we should define these two values which we use as limits. Limits of the interval from which data points, data values will be generated. A and B, two limits, A and B, and all values which are generated, which can be assigned to this random variable having this uniform distribution, are from this range, from A to B. And the main information, the main assumption about this distribution is here, that all values from this range, from A to B, for all values, the probability of appearing them, of occurrences of them, is the same. So when we want to generate values from A to B using uniform distribution, the probability of occurrences for every value from this range is equal, is the same. And this probability density function can be defined in this way, which is presented here. It is a rectangle. So it is a line, and the y coordinate for these points is here. It is 1 divided by the length of this the length between these 2 points A and B. The length between A and B is equal to B minus A. So the inversion of these values, 1 divided by this expression, it is a y coordinate for this line. And the area which we have here under this line, the area always is equal to 1. And this formula causes that this area is always equal to 1. So it is uniform distribution. We can divide this interval from A to B into many subintervals of equal length, and probabilities of belonging values which are generated to every interval is always the same. Is always the same. How to generate values having this distribution? We have this example, the example. It is the same example which was presented at the beginning of our presentation. Here we defined these limits, A and B, and the number of values which I'm going to generate. Here, 10. And we see that 10 values were generated. Please look at this program. I can execute it many times. And we can get different values. Every data set is different. Every vector or list of values has different components. Of course, always the number of elements is 10, but of course I can change it, 20 to generate it. I can change values defining the limit. And we see that during every execution, we can get different set of data. Of course, you can run this program on your computer, and data which will be generated on your computer will be different than data which I obtained on my computer. First, we can think that it is okay, because these values have random character. But we should remember that here, using computer programs, it is not possible to generate real random values. These values which I obtained here are very similar to random values, but they are not random. They are calculated using some mathematical functions. These functions sometimes are complex, and these values which we can calculate using these functions are very similar to random. But there is a formula, and we can find this formula in the documentation of Python language, which is used for calculating these values. They are not random. They are similar to random values. They are called pseudo-random values. Of course, we can say that we generate random values, but we should always remember that these values are only similar to random values. And the function is used for calculating these values. This function uses previous value to generate next value. So this value is transformed using this function to this value. In next step, the same function is used to generate next value using this value. So using this value, we can generate this value, and so on. This function is used many times, and this series of pseudo-random values is generated. Always we use previous value to generate next, to generate consecutive value. But there is a question. We know that, for example, this value was calculating by using this function, and as a parameter, the previous value was used. It is obvious. But what value, which value was used to generate this first value which we have here? Because we don't have previous value which could be transformed to this value. We don't have it. And the solution which is used to generate the first value is very simple. We should use the information about the current time as a first value. So starting Python interpreter, at this moment of starting Python interpreter, the information about the current time from the clock which we have in our computer was obtained, and this value was transformed into the first value. And the first value in our series, this one, was calculated using this value obtained from the clock which we have in a computer as a previous value, as a parameter for this function. And current time is at the moment of starting Python interpreter is different on every computer. Therefore, values obtained by different users are different. This value obtained from the clock, this previous value, is called the seed. And default value for obtaining this seed value is to read this value from the clock, which we have in our computer. But also, it is possible to define this seed. I have in this program this S variable, and it is a seed value. I want to use this value as a seed. And when I want to define this seed value, I should use this seed command. Seed command, and I set this S value as a seed, as a starting point, a starting value for a generator of random variables, of random values. I set here this value 12 as a seed, and I generated a series with 10 values. Maybe we make some changes to it. And after it, now it is a comment, I generated next series with also 10 values. And here I repeated this experiment and generated here the third series. And please look at the example. The first series, the second, the third series. They are, of course, different because the first element in the second series was calculating use was calculated using the previous value which was generated, and this previous value is the last element in the previous series. And of course, we can repeat this experiment many times. But now, please look at the results here. We see 3 series, and all of them are identical. The first series, the second series, and the third series. They are identical. Because in every case, the same value equal to 12 was used here as a seed value, as a previous value, as a value which was used for generating the first element in the series. This element, and this element. The seed value was the same. Then also the series are the same. If we want to generate many times random or pseudo-random values, but if you want to have the same values at every time, we should set the same value as a seed value for every experiment. And then series which will be generated always will be the same. Here, I showed you this mechanism using uniform distribution, but it works for every type of distributions. Please remember about this seed. So if we want, for example, to generate data for evaluation of some models, statistical models, and we have many models, but we want to have the same data set, then for every model, we should generate data using the same seed value. Then data sets will be the same for every experiment. And then we can compare results, the quality of results obtained using different models. It was the first distribution which I wanted to present. Uniform distribution. Uniform distribution, we remember values can be from the interval from A to B, and the probability of occurrence for every value is the same. And we know how to generate it using a random generator. For continuous data, the most popular distribution, it is a normal distribution. Normal distribution has probability density function which is defined in this way. So we see that a function which is used for defining the shape of probability density function may be treated as rather complex. And this function has two parameters, mi and sigma. Sigma, it is a parameter, sorry, maybe first mi. Mi letter, this Greek letter mi here, represents the position of this line. And for example, this blue one, which is here, for this blue one, mi is equal 0. It means that the highest value for this probability density function is for x equal to 0. This shape, this line, this curve is symmetric with respect to this 0 point, and the highest point is for it. Then this we can check. For example, for this green line, mi is -2. -2 is here, and we see that also this highest point is exactly above a value -2. It is the first parameter. And the second parameter, it is sigma parameter. It is a standard deviation, which informs us about the distribution, about the average distance of every value which we have in our data set from the average value, from the mean value. I'm thinking about arithmetic mean, calculated for all points which we have in our data set. Sigma distribution defines the width of this shape, which is used to describe probability density function. We see, for example, here, please compare this blue and this red line. For blue, here on this picture, we have sigma squared. So sigma to the second power value, but so sigma, it is a square root of these values. For this blue line, sigma is equal to the square root of 0.2. For this red, sigma is equal to 1, because the square root of 1 is also 1. It is, in this case, for a red line, sigma value is greater. Then we see that the width of this shape also is bigger. Of course, the highest point, the position of this highest point is smaller with comparison with this blue line. But it is obvious because we remember about this very important assumption about probability density function, that the area under this curve is always equals to 1. If we increase the width, we must decrease the height of this shape to ensure that the area after this curve always is equal to 1, because it is the most important assumption concerning probability density function. When we see that this function can be presented in graphical form, this function always has this shape which is very similar to a bell, and therefore we can call it bell-shaped function. It is probability density function. And here we see cumulative distribution function. We know how to interpret it. We see that for normal distribution, the shape of cumulative distribution function is very similar to S letter. For these elements, for these distributions, normal distributions, cumulative distribution function is presented here. These functions have theoretical character because these lines were produced using only formulas, not data. The empirical distribution in practice is similar to these distributions which are presented here. They are similar, but not the same. They should be similar, but it is difficult in practice to get distributions which are very, very similar to these theoretical. How to produce these plots or plots similar to this one using data. First, how to generate data, random values, which have normal distribution. The function which I used here is here. You can see here it is a function from a random module from NumPy package. And this function has 3 parameters. 3 very important parameters, obligatory parameter. Maybe not obligatory, but the most important for us. Log. Log parameter corresponds to me parameter. It is a value around which values should be generated, values should be distributed. Scale. This parameter corresponds to sigma parameter. And size, it is a number of values which we want to generate. And I generated values. I can execute it many times, and we see that always a series which is generated is the same, because always I use the same value as a seed. After removing this first command, we can see that values are different at every experiment. And data were generated here. I displayed them. Of course, when I have 1,000 data, it is not possible to analyze all these values. And therefore, I produced a histogram to present this data. And we see when I generated data with normal distribution for me equal to 0 and standard deviation sigma equal to 1, then for this data, histogram has this shape. It is a normal histogram with number of occurrences for every interval, and we see that the highest number of elements belong to these intervals which are located very close to 0 value. We see here, of course, we can remove this for a moment. And we see that for every experiment, the shape of this histogram is slightly different, but all of them are similar. Please look at this experiment. After increasing the number of elements, we see that the shape of this histogram is much closer to theoretical distribution. I will try to change it again. Now, of course, it is rather time consuming, but we see that it is very, very similar to this shape. When the number of elements is small, then differences between theoretical and empirical distribution are bigger. But 10,000, it was good value. We see that it is very, very similar. Now, I want to present this probability density function, which was estimated using kernel method. For our data, probability density function estimated using this kernel density estimation method has this shape. Oh, of course, it is the same as here, and we see that for our data, the shape of empirical probability density function is similar to this theoretical. And cumulative distribution function for our data, also we see very, very high probability, very high similarity to theoretical cumulative distribution function. Please look at this histogram once again. We see that here we have intervals. The length of every interval is the same, and we see that probability of belonging values to these intervals which are close to me parameter are higher than probabilities of belonging to these intervals which are far from this me value. Of course, for probability density function, we see that values here which we have on y-axis are different to ensure that a value under this curve is equal to 1. And it is normal distribution. Now maybe we make a short break, about 10 minutes, and at 10:30 we will continue with t-student distribution. 10-minute break. I think that we can start after a short break. And now about t-student distribution. We see that the formula for calculating probability density function is very complex. It is very complex also because here we see very complex gamma function. But the shape of probability density function is very similar to normal distribution. We also see here that cumulative distribution function for t-student distribution also is very, very similar. So we should remember that t-student distribution is very similar to normal distribution. I have here the comparison. Here you see this picture with comparison of t-student and normal distribution. Normal distribution, it is blue. T-student distribution, green. We see that they are very similar. We see only two differences. The first is here. The position of the highest point. For normal distribution, it is slightly bigger value. And the second difference we see at the ends of this graph. Here, this line, green line, for t-student distribution is higher than for normal distribution. But differences here and here are not big, rather are small. But t-student distribution is very useful when we are talking about verification of statistical hypothesis. Therefore, we should remember about this distribution. How to generate values from this distribution? We have here two commands. The first command, it is for creation of the object defining this distribution. And this distribution has two parameters. Degree of freedom, it is A parameter, and B, location parameter. Location parameter, it is similar to me parameter in normal distribution. For example, here I assign these values 4 and 3 to A and B, and the definition of this distribution is here. When I want to generate values from this distribution, I should use this method, RVS method, random values. I think that it is from this expression, to generate random values. The number of values which should be generated is defined here. A and B were defined here. And of course, we can display these values. And also, I generated these two plots with PDF and CDF, cumulative distribution function. But sorry, it is not, of course, it is not theoretical, it is empirical, because it is based on this data. And these functions are very similar to normal distribution. We know that this student distribution has two parameters: degree of location, degree of freedom, and location parameter. How these parameters work? This location parameter. This location parameter is defined here. For the first probability distribution function, it is 3. For the second, it is 4. And we see that it works in the same way as me parameter for normal distribution works. For example, I can change it to 6 maybe, and here the range I change to 12. And for first data set, this location parameter is 3, and exactly under the 3 value, this probability distribution function has the highest point. For the second, it is 6, and here under the 6 value, we have the highest point. And number of freedom. Number of freedom, it is a parameter which is very similar to sigma parameter. So the shape of this line, this bell curve, we can define changing this parameter. On this plot, I have 4 different curves for degree of freedom equal to 1, 2, 5, and 10, and we see differences in the shape of this curve. But generally speaking, t-student distribution is useful for calculations which are necessary for performing statistical tests. It is rather, sometimes it is useful also for description of real data, but mainly in statistical tests. And the last distribution, which I wanted to present, beta distribution. Probability density function is presented here. For this beta distribution has two parameters, alpha and beta. And we see for different values of parameters, different shapes of probability density function. We can change these parameters, and for example, it is possible to obtain this shape, which is very similar to normal or t-student distribution. This purple line, which we have here. This purple line, it is for these parameters equal to, both parameters are equal to 2. Cumulative distribution function is presented here. Also, we see for different values of these parameters. So shapes may be different. This plot may be symmetrical or not. It depends, of course, on parameters. But there is something very interesting for this distribution. Probability density function has values different from 0 only from the range from 0 to 1. Here, on the right to the side of 1 and on the left side of 0, values of probability density function are always equal 0. And it is very important because therefore this beta distribution can be used for describing probabilities. Because we know when we are talking about probability, probability is always from 0 to 1. It is not possible to have probability lower than 0 or higher than 1. When we know the exact value of probability, we can present this exact value. For example, probability of something is equal to 0.7. But very often we don't know the exact value of probability because it is a random variable. We can treat probability as a random variable. And then we should describe the behavior of this random variable and using, of course, probability density function. If we want to do it, we should use beta distribution because it is the only, maybe not the only, but this distribution is defined. It has probability density function values greater than 0 only from the interval from 0 to 1. It is not possible to use normal or t-student distribution for defining, for describing probabilities, because we see that also values which are outside this range from 0 to 1 can appear. Only this probability is useful for this, only this distribution is useful for describing probabilities. How to generate values using beta distribution? Examples here. Parameters defined for defining this distribution are here, and I here wanted to generate 1000 values using these parameters alpha and beta. These values are from beta distribution. Of course, I can display it, but it is not interesting. It is similar to values which I had above. But the best way of describing this data, it is probability density function. Also, sorry for it because I had copied from another example. It is probability density function, empirical, of course, calculated using a data set, and it is cumulative distribution function. When I want to calculate and to plot theoretical distribution for a theoretical probability density function, I can use this program, and we see the shape here. It is the shape for the same set of data. Please look at, I can change beta, for example, to 5. And we see that in this case, the values are the empirical density, probability density function is not symmetric. It has this shape, and also theoretical. Also, we see that these values were not calculated using this data set, but they were calculated using oh, I don't have a formula, but very complex formula defining probability density function and cumulative density function. So here we have empirical, here theoretical. And at the end of this part of our meeting, I'm going to present you very important theorem, central limit theorem. It is very important rule. It states that the sum or average of large number of independent and identically distributed random variables will be approximated using normal distribution. I prepared a program which may allow us to interpret this rule, this theorem. Please look at this program. Here I produced a series of data, a series of values which were generated from uniform distribution. And the range is from 0 to 10. I generated 1,000 values. And here I prepared a histogram. And we see these values were from 0 to 10. We have 0 values to 10 value here. These values, this range was divided into 10 intervals, and the number of elements, values in every interval was calculated. It is similar to uniform distribution. Of course, we can change the number of elements for more values. The similarity to uniform distribution should be higher. Of course, we can change it to 100,000 elements, and now we see that for every interval, the number of elements belonging to this interval is very, very similar. So we have data from uniform distribution. It is not normal distribution. It is uniform distribution. And now, many times, many, it means 100,000 times, this code is repeated. From this data set, in which we have data uniformly distributed, I randomly selected 100 values. So 100 values from this data set I selected. randomly, completely randomly. In every loop or in every iteration of this loop. For these values, which I have in this set, for these 100 values, I calculated average value, mean value. And this value, this mean value is here. And I wanted to store all these mean values. I append them to the list which was created here. So we can check int ints. Of course, it is possible to print it. It is rather time consuming because this loop is repeated 100,000 times. And for every loop, I selected randomly 100 elements and I calculated an average value for them. I think that we will get the result very shortly. I checked this program yesterday and it was calculated in 20 seconds. Now, when I use Microsoft Team program, I think that I see that it is much more difficult, but I hope that shortly all calculations will be finished. It is too difficult for my computer, but it is caused by transmission using Microsoft Teams program. And now I don't know what to do, if I should interrupt it or not. Maybe we will wait till 5 minutes, and if okay, it was two. For 1000, I think that it will be easier to calculate. Yes, we have these values, and here we see the distribution. So for every experiment, for every iteration, I calculated mean value for this subset, which was randomly chosen from values which have uniform distribution. And all these means values stored on this list. So for every iteration, the average value for these 100 elements is here. During the second iteration, I got this value. During the third iteration, I have the result here. And I have these average values, these means values. And now I presented a distribution of these mean values, average values. And we see that it is not uniform distribution. It is normal distribution. And now I think that this theorem is clear. We have a data set, and it is not important the distribution of the data in our data set. In our example, which we calculated, we have data taken from uniform distribution, but we can generate them from any distributions. It is not important. And after many repetitions of a procedure in which we selected randomly some elements from this data set and calculated average value or sum of all elements which we have in this subset, these elements, these average values or these sum values always have normal distribution. And it is the illustration of the way in which this theorem works. The distribution of our primary data was uniform. After selecting randomly subsets and after calculating for every subset mean value, here I calculated mean, average value, arithmetic mean. But of course, I can calculate sum of all elements which I have in this subset. These means or these sums always has normal distribution. It may be strange, but it is true. Of course, it is not a formal proof, but it is possible to prove this theorem. It is only the illustration, which shows the interpretation for this very, very important in statistics rule. And now I think we can start the second part of our meeting about statistical hypothesis testing. How to test, how to check some hypotheses, if they are true or not. It is a very important element of statistical data analysis. It is very important tool which we can use for verification of some thesis, of some hypothesis, which we can formulate. It is not for discovering of some patterns. It is not for identification of some rules. It is for verification. And it is the main difference between classical statistics and exploratory data analysis. Now, very often we use exploratory approach. And we want to identify, we want to find some rules, some regularities in datasets. And we have no assumptions about them. It is exploratory approach. We want to discover these regularities, these rules, these relationships. Before our experiment and before our calculations, we have no knowledge about them. We try to find them using datasets. It is the main idea of exploratory data analysis. To find some regularities, to find some previously unknown regularities. It is exploratory approach. But the role of classical statistics is different. The main goal was the verification of some statements. It is not discovering some regularities. It is for verification if the regularity which we described is true or no. So we should have hypotheses about these regularities. But we are not sure if our hypotheses are proper or not, if it is true or not. And we use statistical methods for verification of our hypothesis. And this approach, it is the main approach is in mathematical statistics. It is very, very, very important. Statistical hypothesis testing. We want to confirm some assumptions concerning our reality. And the second element, also very important. This second element is related to the two concepts, population and sample. We want to formulate and verify some hypothesis concerning the whole population. For example, concerning all people living in a given country. For example, all people living in Croatia or in Poland. We have some statements about all people in the whole population. We are going to formulate and to verify some regularities concerning the whole population. It is our goal. Verification of some statements concerning the whole population. But we are not able to check, to perform research among all members of this population. It is our second very important assumption. We want to say something about the whole population, but it is not possible to check every member of this population, to analyze the situation of every member of this population. Therefore, we want to create a sample, random sample. It means that I'm going to choose randomly some elements from this population. For example, I'm going to say something about incomes of people living in Croatia. But it is not possible for me to ask every person living in Croatia, to ask every person living in Croatia. And therefore, I decided to make a sample, to choose randomly a group of people from Croatian inhabitants and to create a sample. And for me, it is possible to to make some research and to perform some calculations on data concerning this sample. I can ask them about, for example, their incomes. And I have knowledge about members of this sample, random sample. And having this data, I want to say something, but not about this sample, but about the whole population. It is the main idea of statistical hypothesis testing. For example, the average monthly income of one person in Croatia is about 2,000 euro. It is my opinion about average income in Croatia. And I want to verify it because I don't know if it is true or not. I know that I'm not able to ask everybody in Croatia about his or her income and to calculate the average value. It is not possible for me. Costs which are related to this procedure are too high. Therefore, I decided to select randomly, for example, 1,000 people. And I have this sample. And I ask everybody from the sample about their income. And I have the information. And I see that the average income in this group, in this sample, is for example, 2,055 euro. And having this data, can I say that average income in Croatia, monthly income, is 2,000 euro or not? Is my hypothesis, which I have at the beginning, is true or not? But it is a hypothesis concerning the whole population. So to conclude, the main goal of statistical hypothesis testing is to verify some statements about the whole population in the situation when it is not possible to conduct calculations using data describing the whole population, but it is only possible to select randomly a sample from this population to perform some calculation using this sample and use these data, these results of this calculation to say if our hypothesis is true, if our hypothesis concerning the whole population is true or not. It is the main idea of statistical hypothesis testing. How to perform this procedure? First, of course, we should state our hypothesis about the whole population, because we should have this sentence which we are going to verify. We should have two hypotheses. The first one, it is a zero hypothesis and alternative hypothesis. This zero hypothesis says that something does not exist, that something is not true, that something is not important. For example, I'm going to say about average income of people in a given country, and I can say I should formulate this hypothesis. This zero hypothesis, that the average income is, for example, equal to zero, or that the average income is equal to 2,000. And alternative hypothesis, that it is not true what was stated in the zero hypothesis. It is the first step. Definition of these two hypotheses. The first one, it is a hypothesis which I'm going to verify. And the second one, it is a hypothesis which is opposite to this which we have as a zero hypothesis. When we want to conduct this procedure, we should check some assumptions. In different procedures, these assumptions are different, but it is necessary to check them. These assumptions which are listed, which are defined for a given procedure. It may be different, but very often they are related to the distribution of a data set. After it, we should define a test statistic. In this presentation, this value is represented by this S symbol. For every test, statistical test, we should the information how to define it, how this S value is defined. And also, we have the information about the distribution of this value. For example, we have that this S statistics has normal distribution. We must know the distribution of test statistics. And next, having the information about the distribution, we should define the significance level. The significance level, which is represented by this alpha symbol. If we know the distribution of our statistic, test statistic, we know that the area under this curve is always equal to 1. And this significance level can be interpreted as an area which we have here at the ends of this probability distribution function. Here, these areas are marked using this orange color. It is a significance level. It is a significance level. How to interpret it? We know the formula, which is used for calculating a value of this test statistic, and we know the distribution of this statistic in the situation if zero hypothesis is fulfilled. If it is a true what was stated as a zero hypothesis. We know this distribution. Then probably for our data set, a value which we can get using our data set will be in this blue region. If zero hypothesis is true, then a value of our test statistic calculating using data from our data set should be in this region, which is here marked as blue region. It should be here. If it is outside this region, in this area, which are marked here using orange color, then it means that probably our zero hypothesis is not true. And we should reject this hypothesis. So we should calculate this S statistic using our data set, and after it, we should make a decision. If this S value calculated using our data set, it is denoted here by SOBS. If it is in critical area are at the ends of this distribution. If this value is in these two orange, if one of these orange parts, then we should reject zero hypothesis. If it is not in this area, so it is in blue area, we have no reasons to reject the zero hypothesis. It is a classical approach which we can use when we are going to perform statistical tests. So first, we should calculate these values at which these critical regions, critical areas start. And after it, we should calculate this S value using our data set and check if this S value is in this orange area or in this blue area. If it is in this orange area, we should reject zero hypothesis. If it is in blue area, we have no reasons to reject zero hypothesis. The idea is simple, but there is one problem with it. How to calculate this value which we have between this orange and blue area, and on this and on this side. It is sometimes difficult. And many years ago, we used some tables with values for different distributions, and we calculated it. But it was rather boring. Now, this traditional procedure, which I presented here, was changed, and we use another procedure. Of course, maybe I should say it in another way. We should the same procedure, but we use another values, which we use during decision-making process. Then these steps, step number 6 and number 7, we can reformulate. And here we have another formulation of these rules which we had. We should, of course, having our data set, having our sample, we should calculate these statistics, and we should also calculate p-value. P-value, which is defined in this way, which we see here. It is the probability that obtaining value of test statistic or higher value, it is probability of obtaining the calculated value of S statistics or higher value. It is a probability that we obtain this value or higher value. Maybe it is not exactly the truth, but we can say that p-value can be interpreted as a probability that a regularity which is stated in zero hypothesis is not true. And the last step, it is a step concerning the decision. And when we use p-value, our rules are very simple. If p-value is less than the significance level, we should reject zero hypothesis. If no, there is no reason to reject zero hypothesis. It is a description of the procedure of statistical hypothesis testing. I know that for some of you, it may be very complex. So I'm now going to show you how to use these procedures in practice. Today, I'm going to show you some tests, some statistical tests, and of course, I'm going to focus on practical aspects of using these tests. First, I'm going to show something about t-tests. T-tests are used for verification of some facts relating to mean value, average value in the whole population. And there are three types of t-tests. T-test for one sample, for two samples, and for one sample in which every member of this sample was observed in two moments of time. First, about one sample. It is a hypothesis saying that the mean value in the population is equal to a specific value. So zero hypothesis says that mean value is equal to the specific value. And alternative hypothesis says that, of course, it is not true. That the mean value, it says that the mean value is not equal to the specific value. And statistic, test statistic, which is used for this test, has its form, and the distribution of the statistics is defined as t-student distribution. Statistics is here. It is the average value for the sample, and here for the population. X, this symbol, it is the average value which was calculated by us. And here it is a value which was specified, which was defined by us. And we want to know if the difference between these two values is big or not. Of course, in zero hypothesis, it was said that the average value is equal to this value which was defined, which was specified by the user. But of course, we can reformulate it and to check if the difference between these two values are equal to zero. It is normalized using this formula. It is with statistics, but of course it is not possible to calculate these values. It will be done automatically. Here I have a data set. A data set, artificial data set. It is a series of, for example, maybe 300 values we have taken from normal distribution, and me is 5 parameter and standard deviation is 1.5. These values here were generated. Here I calculated the mean value. And here I'm going to check if the average value in the population is equal to 5. Of course, here I have a sample. Now, I'm going to use this test to check, to verify my hypothesis that the mean value in the population is equal to 5 using this data. And I use this statistic, I use this command for performing all calculations. T-statistics is here, but for me, this value, p-value, is the most important. If it is smaller than significance level, in practice, significance level is defined as 0.01 or 0.05. So this it defines this area which are in critical, these areas which forms critical area. And here we have this p-value. It is higher than significance level. Then, if it is higher, then there are no reasons to reject the hypothesis. Zero hypothesis. Zero hypothesis here is that the mean value for the whole population is equal to 5. I used this test. I got this p-value, and I see that there is no reasons to reject this hypothesis. And now I'm going to check if the mean value in the population from which this sample was got is equal to 6. Please look at p-value. It is very, very small. So we should reject zero hypothesis. We should reject zero hypothesis, and zero hypothesis which was formulated in this way, saying that the average value for the whole population from which this sample was generated, was selected randomly, that is equal to 6. It is the first example. Maybe we make short break, maybe 5 minutes, and after 5 minutes we will continue. I think that we know the procedure, how to perform statistical tests. We should know how the zero hypothesis is defined, how the alternative hypothesis is defined, and we should this hypothesis about the whole population. We should have a sample data, calculate some statistics, and calculate p-value, and compare this p-value with significance level. If p-value is smaller, then we should reject zero hypothesis. Is smaller than significance level. If p-value is not smaller than significance level, we have no reasons to reject zero hypothesis. Maybe the last element which can be discussed here using this example, another way of interpretation of p-value. You know our problem. We have the population, and I'm going to verify the hypothesis that the average value of this variable, which I'm going to analyze, and the whole population is equal, in our example, is equal to 6. It is my hypothesis. If this mean value is equal to 6, I'm going to verify it. So I selected randomly data from the whole population. In our example, instead of selecting randomly data, I generated it, but of course, in real situation, this data should be selected randomly from the whole population. And I'm going to use this data set to verify my hypothesis that the mean value in the whole population is equal to 6. I performed all calculations and I obtain this p-value. How should I interpret this value? I think that this way of interpretation may be the best. It is a probability. P-value, P from the word probability. It is a probability of obtaining this data set, which I have as a sample, in the situation in which the zero hypothesis is true. Assuming that zero hypothesis is true, then the probability of obtaining this data set is here. It is very, very low, very small. We see that when we have this hypothesis, that the mean value is equal to 6, and when I selected randomly this sample and calculated these values, I obtain very low probability. It is a probability of confirming this hypothesis by this data set. It is very, very, very small. In the case when the mean value for the whole population is 5, then the probability, of course, we can get different values for every calculation because we have random values here. Then the probability of obtaining this data set as a sample is high. Therefore, we have no reason to reject this zero hypothesis. It was the first form of t-test. We use this test when we want to check if a mean value for the whole population is equal to a specific value. But I think that the most popular version of this test is presented here. It is t-test for independent samples. In this case, we have two populations. For example, all people living in Croatia and all people living in Greece. And we want to check if it is true that the average income in Croatia is equal to the average income in Greece. So also in this case, also our hypotheses are related to the whole population. To check it, we selected randomly two samples, one in Croatia, one in Greece. And we calculated statistics, statistics for this test. This statistic has this form which we see here. It is a comparison of these two average values. It is, for example, for Croatia, it is for Greece. And we want to say if these two values in the whole populations are equal or not. For example, a sample data from Croatia is here. Of course, it was also generated randomly. A sample from Greece is here. Also, it is generated randomly. These values were taken from normal distribution. Standard deviation is the same in both cases. Only me values, location parameters are different. And we are going to verify our hypothesis that average values in these two countries are equal. And probability p-value, which was obtained, is here. It is very small. And the way in which we can interpret this value is the same as in the previous example. Assuming that average values in Croatia and Greece are equal to each other, then probability of obtaining these two samples from these two populations is here. So it is very small. There is no chance to obtain these two samples in these two in these two countries when the average mean values are the same. And here also, I will check its value. And now probability is very high. In this case, these data sets confirm my hypothesis that mean values in these two countries are the same. When we want to perform this t-test for two populations and, of course, two samples, we should use this function which I use here. And the third situation. The situation also is very important. For example, in medicine, or also in education activity. We have some objects, and we check a value of a given variable for every object twice. For example, before and after medical treatment. And we want to check if there is a difference between these two observations. When we are talking about medical treatment, if there is a difference, it means that this treatment has the impact on this feature which we analyze. And it is a test in which we are going to analyze differences between, for every object, differences between these two values. One of them which was obtained at the beginning, and one of them which was obtained at the end of a period of time. It may be useful for analyzing of medical treatment. It may be used for analyzing teaching activity. For example, the number of points obtained by students before and after some lectures. Of course, after some lectures, the number of points should be higher. And here I have some, of course, here we can find some formulas, how this statistic test is defined, and the examples here. For example, we have 300 objects, 300 students. And in this vector, data 1, we have number of points obtained by every student at the beginning of this educational process. And these values are generated here. Here we have a data set, a data 2 data set, and it is defined in this way. So it is data 1 plus random values obtained from this distribution. So we added some random values which we got from normal distribution to these values which we had at the beginning of this period. And we see, so we see how this sample was defined, and we can perform it. And we see here a p-value. Our zero hypothesis says that at the beginning and at the end of this process, educational process, the results, the average results are the same. And for this data, we have no reason to reject this procedure, because these values which I added to these which we had at the beginning are from normal distribution, and the average value for this difference is 0. But when we change it to 1, we see here this p-value is very small. In this case, we see that this educational process has a huge impact on our students. We see that values which we have at the beginning and at the end of this educational process, at the beginning and the end, for example, of a course, are completely different. This data which we obtain does not confirm the hypothesis that the average number of points obtained at the beginning and the end of this course is the same. The same procedure we should use, and very often we use, for analyzing the impact of medical treatment. We can measure some parameters for every person at the beginning of this treatment and at the end of this treatment. And we want to compare if average value of these parameters is the same at the beginning and at the end. We use this test to check it. So it is a t-test for the situation when we have two values for every object, two values taken in different points of time. And we want to check if there is a difference between these two values or not. And what to do when we have not two groups, when we are talking about, maybe we should back to this situation, t-test for independent samples. Here, we assumed that we have two groups, two populations, two samples, and we compare if average values in these two populations are the same, using, of course, data about two samples taken from these two different populations. But what should we do if the number of populations and samples is greater than 2? Then, instead of t-test for independent samples, we should use test which is called analysis of variance, ANOVA test. The main elements here are very similar. The idea is very similar. We have many populations, people from different European countries. And our zero hypothesis is that the mean value in every group, in every population is the same. For example, our hypothesis is that mean average income in every country is the same in Europe. It is our zero hypothesis. And our alternative hypothesis is that it is not true that average income is the same in every European country. It means that at least at one country, this average income is different from incomes from other countries. And we have a situation here for 3 countries. In every country, a random sample was chosen, and these samples are here. Of course, they are not chosen, they are generated. We see the way in which they were generated. And my hypothesis is that mean value calculated for every population is the same. I calculated mean values for every group. Of course, it was performed by this procedure. And here we see p-value. P-value that which is rather big, rather big. So it is, there is no reasons to reject the hypothesis that in these three countries, average values are the same. But we can change one sample, maybe in this way. P-value is 0. Therefore, I should reject the hypothesis that average values are the same in every country. At least at one country, it is different. Of course, I can change also this value. And also we see that these three data sets does not confirm this hypothesis that mean value in every country is the same, is equal to values in other countries. Here I wanted to show you some procedures which we use to perform calculations. But maybe you remember that at the beginning, I said about some assumptions. It is allowed to use these tests or other tests because a number of tests different statistical tests is very, very huge. We can use them for verification of many types of different hypotheses. And very often we have an assumption that data in the population should have normal distribution. It is a very popular assumption. And how to check it? How to check the normality of distribution? There is many tests which we can use for checking normality of distribution. But the most famous test and most popular, it is Shapiro-Wilk test. We have a data. Here, this data were generated randomly. So also, we should think about this data as about a random sample. We can imagine that we have a population. In this population, we have a lot of data. It is not possible to check every element from this population. Therefore, we selected randomly some elements. We created this random sample. In our case, we did not selected them randomly, but they were generated. So it is an artificial sample. I used normal generator for normal distribution. Parameters are here, mi and sigma. Number of elements in this sample is 1000. And I'm going to check if this variable in our population has normal distribution. So I selected, of course, I want to verify this thesis, the hypothesis, using this data which I have in our sample. I used Shapiro-Wilk test. This procedure is for it, using this data, and the results are here. Here we see statistics, which is used here, but maybe it is not important in this way. The most important element is here. P-value. P-value is 0.5. It is higher than significance level, because significance level very often, as I said before, is defined as 0.01 or 0.05. It is the area of this critical region, critical area, which we have for probability distribution function. It is huge. So there is no reasons to reject this hypothesis. We can say that data which we have in our data set, we assume that it is, of course, a sample, do not confirm that the probability that this data which we have confirm our zero hypothesis. It is the probability that, assuming that in population, in the whole population, this variable has normal distribution, the probability of obtaining this data set is rather high. And the second experiment. Now, our sample has different form. These values were generated using uniform distribution. It is not normal distribution, of course. And of course, it is my sample. And I want to verify the hypothesis that in the whole population, variables of this, values of this variable have normal distribution. I use the same procedure for performing Shapiro-Wilk test, and the result is here. P-value is very low. It means that I should reject zero hypothesis. Zero hypothesis stated that this variable, which is represented by the sample, has normal distribution. We see that it is not true. We know how we can describe random variables. We know how to use the information about it to perform statistical verification of hypotheses. Of course, as I said before, the number of different tests is very huge. These tests which I presented here, we can treat as examples. In all these examples, which we discussed today, we use only one variable. And we have some hypotheses about values of this one variable. But average value is equal to something, or if this variable in two different populations have the same average value, or has not the same average value, but always these hypotheses were related to one variable. And now I'm going to say something about some words, some remarks, because I'm going to continue this topic tomorrow, to say something about the analysis of relationships between two variables, two or more variables. We have two variables, x and y, and we want to calculate relationships between them. How we can do it? The first way which we can use is based on covariance value. It is a measure which we can use for describing relationships between values of two variables. It is the sum of these products. For every data point, we should calculate this product, and after it, we should add all of them. And at the end, we should divide all values by n, and it is a number of objects, number of observations. What we have here, it is a product of two values. And these values are defined as differences between a value of x variable for a given object and average value calculated for this variable for all objects. And here the same situation, but with the second variable, y variable. A variable for a given object minus an average, a mean value for all objects calculated for this y variable. Average value, it is a value which is in the middle, in the center of this range from which we have data for x and here for y variable. It is the difference between a given value and the average value. It may be negative or positive. If it is positive, it means that a value, a given value for a given object, a value of this variable is greater than average value. Then it is, of course, positive. If this expression is negative, it means that xy, it means a value of y variable for y object, for a given object, is smaller than the average value. If for x variable we have here positive value, and for y variable also we have positive value, then the product of two positive values also is positive. If here we have negative value and here negative value, the product is positive. When one value is positive and one negative, the product is negative. These rules are very necessary when we are thinking about the interpretation of this coefficient. Please look at this data set. We have, for example, x here and y here. I know they are here described as x1 and x2, but when we are thinking about this formula, we can imagine that we have x variable here and y variable here. For x, we calculated average value. It is, I think, 0. For y also, we calculated we calculated average value, and also it is 0. So average values are equal to 0 for these two variables. And now, please look at this situation. Now, when for this object, maybe not for this, maybe for this object is here, and this difference, when we are thinking about x variable, is positive, because this coordinate is greater than 0. Y coordinate also is greater than 0. Also it is positive. And we have the product of these two positive values is positive. Here, for example, for this object, all these factors are negative. The product is positive. Then, after summing up all these values, when this sum is positive, it means that data are located in this way, which we see here on this picture. For a given object, if x coordinate is big, it means that also y coordinate is big. If x is small, it means that also y coordinate is small. In this situation, we can say that covariance value for these two variables is positive. I maybe made one change here in this program. Now we have different situation. When x is greater, then y coordinate is smaller. If x is smaller, then y is greater. And general position of these points is presented here. In this case, covariance is negative. We see that the covariance is very useful when we want to describe relationships between values of two variables. We can interpret covariance only if it is negative or if it is positive. There is no lowest and highest value for covariance coefficient. If we want to normalize it, we should divide this covariance value by standard deviations calculated for the first and for the second variable. In this way, we can calculate correlation coefficient, which was proposed by Pearson. Therefore, it is called Pearson's correlation coefficient. And it is the most popular measure of relationships between two variables. Values of this measure are always in the range from -1 to +1. Plus high values, very close to +1, they inform these values inform us about strong positive correlation. Low values close to -1 inform us about strong negative correlation. Values which are close to 0 are inform us that there is no correlation, no relationships between values of these two variables. How it works in practice. I'm going to show you how it works using this artificial data set, but this artificial data set which we can see here. But to generate this data set, we should use another generator. It is not possible to use twice generators which we used previously for generating X and Y coordinates. We should use multidimensional generators. And here I'm going to show you how to use generator for multidimensional normal distribution. Multidimensional normal distribution, it is a distribution which is defined by two parameters. Of course, multidimensional normal distribution is similar to one-dimensional normal distribution, which we presented earlier. Because in our earlier examples, I use one variable. Therefore, I can say that it is one-dimensional normal distribution. Only values for one variable were generated. Now I'm going to use some methods for generating points in two-dimensional space or three or higher dimensional space. It is an example for two-dimensional space. And for one variable, we had two parameters, mi and sigma. Mi, which was used to define the location of these points, and sigma, which was used for description of distribution of points in the region which was defined by location parameter. Similar situation we have for multidimensional normal distribution. But now the number of parameters is also 2, but we have these parameters have different form. We have here in this example two-dimensional normal distribution. Two-dimensional normal distribution, it means that every object is defined by two features, two attributes. These attributes are used here as coordinates for these points. Then we can say that every point represents one object. The first parameter, it is a mean parameter. Mean parameter for the first and for the second variable. In this example, it is here, mean parameter. The first value, it is a mean value for X, the second for Y variable. Now I have 0 and 0. I can change it for 5 and 7. For X, 5, 7. Mean value represents a point which is in the center of our data set. 5, 7, it is here. 5 and -7. 5 and -7, it is here. The meaning, way of understanding of mean parameter, I think, is obvious. I will change it to 0, 0. And the second parameter. It is a variance-covariance matrix. And now it has this form. In the first row, 1, 0, and the second, 0, 1. We talk about this variance-covariance matrix, and we know that on the main diagonal we have variances. Variances which we can use for calculating standard deviations. Standard deviation, it is a square root of variances. And standard deviation for x variable, it is a square root of 1. It is 1. And standard deviation for y also, it is 1. Standard deviation can be interpreted as an average distance from the average value. We are now thinking about x coordinates for all points. The average value is here in 0, and we can calculate distances between 0 value and x coordinate for every point, and having these distances, we can calculate average distance, and it is equal to 1. Here, the second value, it is for y, the same way of interpretation. Then we see that the average value of y coordinates of these points from 0, because we have also mean value in 0, also is 1. We can change, of course, it. And now we have variance-covariance matrix of this form. For x distances, average distance from average value equal to 0, for x coordinates is 1, and for y it is standard deviation is square root of 3, it is 1.72 or 3. We see that for y value is bigger, and now we see that this data set has different shape. Here we have variances, and also I think that you know how to interpret them. But now covariances. Now, next example. Here our variance covariance matrix has this form, which we see here. These values, which are out of main diagonal, define covariances between the first and the second variable. They are positive. It means that points are located along the line which we have in this direction. And the last example. Now we have negative covariance value. This matrix must be symmetric. So this value always must be equal to this value. Now we have negative covariance when the value is when points are located along the line which we can draw here. Now I think that you know how interpret parameters of multidimensional normal distribution. To define this distribution, we use this command, and to generate data set, we use this command. Here, for these values which were calculated here, generated, I calculated covariance, variance-covariance matrix, and we can compare values which I use defining this generator and values which I obtained using this data which were generated. These matrices are similar, but not the same, of course. And also, when we increase the number of values, then the difference between this theoretical and this empirical matrix, the difference will be smaller, similarity will be higher. And we also remember this formula. It is a correlation coefficient. Correlation coefficient which is calculated using covariance value, but it is normalized to the interval, to the range from minus to plus 1. And we can calculate this for our data set, this correlation coefficient. We see this value here. Of course, it is negative because also covariance was negative. It is medium. We can say that it is medium value. We know it is easier to interpret correlation than covariance because coefficient, because for correlation we know the smallest and the highest value, minus and plus 1. We can say that it is medium value. We can say that we have medium negative correlation. Of course, we have statistical test which we can use to check the significance of correlation coefficient. This test has zero and alternative hypothesis stated in this way, which we can see here. Zero hypothesis says that correlation coefficient is equal to 0. And here we have alternative hypothesis that it is not equal to 0. And for this correlation coefficient, also this p-value was calculated, and in this case, it is 0. It means that I should reject 0 hypothesis. It is not true that correlation here, that correlation here is equal to, maybe not here, in general population, because we treat these values as samples. When we are talking about statistical verification of hypothesis. But in this case, it is difficult to say that the covariance or correlation exists between values of these two variables. Now, correlation is very, very low. P-value is high, is higher than significance level. Then we should, that there is no reasons to reject the 0 hypothesis. Therefore, probably we can say that there is no correlation, no relationships between these two values. And the last element for today, simple regression models. We know here that, but I will use, to give this example. We see that here there is a relationship between values of these two variables. Of course, it is not true that correlation coefficient is equal to 0. There is a relationship. How to describe this relationship? There are many possibilities, but the simplest and most popular possibility is to build linear regression model. To find coefficients describing a line which we can use for describing this relationship. All objects which we have in our data set are located along this line. And we want to define, to find this line, to find the equation describing this line. This line is defined by two parameters in this case. Intercept point, it is a point at which this line crosses with y-axis. It is the intercept point. And the second element, it is this angle which we have between this line and x-axis. This angle defines the slope. And intercept point is defined by, here at this picture, as W0 parameter. And this slope is defined by W1 parameter. It is the relation of these two lengths of these two parts of this triangle. So it is a tangent of this angle. It is a way in which we can interpret this W1 parameter. And for our data set, because our data set, which was calculated here, it has a form of a matrix. And this matrix I use here for not here, but here, for calculating these values. Intercept is here, coefficient W1 is here. Then we see an equation describing this line in this form. It is y, which is equal to W0 parameter plus W1 multiplied by x. It is a general form. And tomorrow we are going to talk about this and other forms of description of relationships between different variables. Because as I said at the beginning of our meetings, first I wanted to say something about descriptions of relationships between objects, and therefore we use cluster analysis to do it. And today I'm going to use regression function to describe relationships between variables. But we will continue it tomorrow. So that's all for today. Thank you very much for your participation, and I would like to invite you for tomorrow. Thank you very much.